This lesson is on section 3.2, the first part, logarithmic functions. For x greater than 0 and 0 is less than a not equal to 1, y equals log base ax if and only if x equals a to the y power. Now, this is the definition of the logarithmic function. So definitely write it down, make sure you understand it. The function given by f of x equals log base ax is called the logarithmic function with base a. Every logarithmic equation has an equivalent exponential form. Y equals log base ax is equivalent to x equals a to the y. Alright, that's all a logarithm is. It's an exponent. Now, an exponential function is written this way, y equals a to the x. Logarithmic function is written this way, y equals log base ax. And that, of course, is equivalent to x equals a to the y. So you could think of it as, or say it this way, that y is the exponent you have to raise a to in order to get x. This is a graph of the logarithmic function. Notice it has a shape that's similar to the exponential function, but actually goes through the x-axis instead of the y-axis. We're going to look a little bit more at this later, but for now, just look at this shape. Make sure that you write it down, because you'll need to refer to it. This is the basic logarithmic function. Now we're going to look at some examples. We're going to write the equivalent exponential equation and solve for y. So in this chart we have on the left logarithmic equation, in the middle equivalent exponential equation, and then the solution. And the reason we're going through this is just to kind of help us understand how logarithms relate to exponential functions. So our first example, y equals log base 2 16. You can think of it as this, is that 2 has to be raised to the y power to get 16. And that's why we can simply write it this way. It's completely equivalent. Y equals log base 2 16 is the same as writing 16 equals 2 to the y. And the solution is 4, because 2 to the 4th power is 16, so y equals 4. Y equals log base 2 1/2. Now you should pause this video, try to do the next two on your own, and then resume when you have the answers. So you should have gotten 1/2 equals 2 to the y is the equivalent exponential equation. And then finally, 1/2 equals 2 to the negative 1 power. Therefore, y equals negative 1. Another example, y equals log base 4 16. Again, pause the video, do it on your own, and then resume. So you should have gotten 16 equals 4 to the y power, and the solution 16 equals 4 squared, y equals 2. And our last example, y equals log base 5 1. Pause and then resume. You should have gotten 1 equals 5 to the y power, and therefore y equals 0. The base 10 logarithm function f of x equals log base 10x is called the common logarithmic function. Now, the log key on a calculator is used to obtain common logs. So you should be able to find that on your calculator. Most calculators have a log function and an ln function. We're going to be using ln later. But for now, you should find the log function on your calculator. Now we're going to do a little practice on the calculator. So you're going to calculate some values here. So first, evaluate this on your calculator. Log base 10 100. Keystrokes are going to be just log 100, enter, and you get 2. And that makes sense, right? Because 10 to the 2 power, or 10 squared, equals 100. Now, the reason we're doing this exercise is just to make sure that you know where the log key is on your calculator and that you understand that that log key implies a log of base 10. How about this one, log base 10 2/5? Pause the video, try that on your own, and then resume. So you should have had log parentheses 2 divided by 5, enter, and that answer is negative 0.39794. Log 10 5 is just log 5, enter, 0.69897. And log negative 4. Try that on your calculator. And you probably got an error. Well, why is that? Because there's no way that you can raise 10 to any power and come up with a negative. Because negatives are simply not in the domain of the logarithmic function. Let's look at some properties of logarithms. You'll definitely want to write these down. The first one is pretty straightforward. Log base a 1 equals 0. And that's because anything raised to the 0 power is 1. Second property, log base a is 1. That's pretty obvious too, right? Because a to the 1 equals a. Log base a to the x equals x. And a to the log base ax power equals x. This is the inverse property. And this is very important because it shows us that the logarithmic function and the exponential function are inverses of each other. And basically what that means is that one function undoes the other. Okay, so let's look first at log base a to the x equals x. And let's kind of convince ourselves of why that's true. So what we see here is we're taking a log of an exponential function. So this is an inverse function of an original function. And we end up with x because, okay, if a logarithm is an exponent, and log base a means what exponent do we have to raise a to in order to get a to the x, well, it becomes obvious that we have to raise a to the x to get a to the x. Okay, so that's why log base a to the x equals x. Take a moment to look at that and convince yourself of it. This simply illustrates that the logarithmic function and the exponential function are inverses of each other. And all that means is that they undo each other. Now let's look at the right side of property number 3. A to the log ax equals x. Okay, well, I can use a similar line of reasoning. Let's start with the exponent first, which is log base ax. What that's saying is the number I have to raise a to get x. Well, whatever that exponent is, If I raise a to it, I get x. Okay, so look at it, relook at it, and convince yourself that that's true. This simply shows that the exponential function undoes the logarithmic function, and the logarithmic function undoes the exponential function. That's why one is the inverse of the other. Our final property, if log base ax equals log base ay, then x equals y. And that looks like, it looks intuitive, doesn't it? Because, you know, log a and log a are identical, and therefore, you know, x and y must be identical. That almost looks like common sense from algebra. So here are some examples to put these properties into action. Solve for x, log base 6 equals x. Okay, well that's an easy one, right? That's definitely 1, because 6 raised to the 1 power is 6. And we use property number 2 for that. How about this? Log base 3 to the 5th. And we ask ourselves, well, what exponent do I have to raise 3 to get 3 to the 5th? Well, that becomes obvious, right? It's 5. And that uses property 3, the inverse property. How about this? Simplify 7 to the log base 9. Pause the video and do it on your own, then resume. You should have come up with 9. Again, using property 3, the inverse property. Now solve this equation. Log base 4, x squared minus 6, equals log base 4, 10. Pause the video, do it on your own, and then resume. And you should have gotten x squared minus 6 equals 10, using property 4, the one-to-one property. And therefore, x equals plus or minus 4. Now let's look at the graph of a logarithmic function. Since the logarithm function is the inverse of the exponential function of the same base, as we said on a previous slide, then its graph is the reflection of the exponential function in the line y equals x. Now, write that down, and then when we see the graph, hopefully that will become more clear. So we're going to start by plotting some points, -2, -1, 0, 1, 2, 3. And we're going to plot these points for the exponential function, 2 to the x, because we want to see the graphical relationship between exponential functions and logarithmic functions. So first we have our 2 to the x, and this is the shape we'd expect, as we covered in previous lessons. It does cross the y-axis at 0, 1. It has a horizontal asymptote y equals 0 because it approaches the x-axis, never actually touches it. And it's written as f minus 1x because that is the symbol for an inverse. Now I know that can be confusing because it looks like an exponent, as if it's f to the -1 power, but it's not. It's simply the symbol for an inverse function. This is the line y equals x. We're drawing it as a dotted line. And this now is the function f of x equals log base 2x. Now notice the relationship between these two graphs. It's kind of interesting. All right, f of x equals log base 2x. We see that in red on the right. And then now referring back to the black curve, f minus 1x equals 2 to the x. F minus 1x is the inverse of f of x. And look how they're symmetrical about the line y equals x. Now, why is that true? Well, since these functions undo each other, the x and y coordinates swap. What's x on one graph is y on the other. What's y on one graph is x on the other. We can see that with the point 0, 1, for example. It's 0, 1 on the exponential graph, but it's 1, 0 on the logarithmic graph. And that's simply because since inverse functions undo each other, the x's are y's and the y's are x's. They swap. Okay, so this is the way that inverse functions are symmetric about the line y equals x. Now, how do shifts and reflections work? Well, they work in a way that's very similar to the shifts and reflections of exponential functions, which we did before. So a vertical shift would be the logarithmic function plus or minus a constant, where plus is up, minus is down. A horizontal shift would be a logarithmic function with the plus or minus constant inside the parentheses, where plus is left and minus is right. A y-axis reflection is log base a with a negative right by the x, and that's an image rotated on the y-axis. An x-axis reflection is negative of the whole function, log base ax, and that gives us an image rotated on the x-axis. So if you like, you can review previous notes to see what effects those shifts and reflections had on the exponential functions, because they're very similar for logarithmic functions. Let's look at an example of a logarithmic function that has shift and a reflection. Graph g of x equals log base 2 negative x plus 1. Now, first it's going to be helpful to graph the log base 2x function without any shifts or reflections. That's usually a good first step with these. And we can see just by looking at this function that it's a y-axis reflection because it's negative x in the parentheses, and it's a vertical shift of 1 unit up because it's plus 1. So let's draw our graph. We have first f of x equals log base 2x, which is like what we graphed on the last slide, and that crosses the x-axis at the point 1, 0. Well, now we're going to take into account that we have a y-axis reflection and a vertical shift of 1 unit up. And taking both of those into account, we have g of x equals log base 2 negative x plus 1. And visually, we can see what's happened here is that the function has been reflected or rotated about the y-axis, rotated 180 degrees, and then shifted up 1 unit. Okay, so if you do have to graph functions like this, usually the first step is just graph the unshifted, unreflected function, and that will serve as a reference point for graphing the shifted and reflected function. Here's the classwork. Please copy these numbers down. You can get a head start if you want before class, but as usual, there will be time in class to work on these problems.